Hi everyone. Welcome to this talk. I appreciate everyone's time. Today I'm going to talk about a work that we have been working on and some ongoing works. I'm going to talk about an upper bound on the parity-breaking scale and how that is related and generated from the dark matter candidate. And this work is being done by my amazing collaborators, Matthew Baldwin and Keisuke Harigaya. They are both in University of Chicago. So let's get started. Uh, I'm assuming this is a party workshop, so I'm assuming everyone has been listening to this kind of things over and over. So I'm going to just go very quick. Let's talk about strong CP problem. We know that is in long-standing problem for the standard model. We know that there's in general could be a theta S in the GD tutor operator. This could be violating CP, and this is a theta F in the Yukawa matrix. So if you perform a field redefinition and rotate this kind of field, and you can rotate theta F and theta S into each other, but the sum of them is physical. So you expect there's a physical CP value interface, but the experiment is simply telling you no. Is upper limit is very stringent, and the question is why we don't have it if it seems to be allowed. So this is called a strong CP problem. And parity is one very interesting solution that has been there for 30 years or 40 years. I don't remember the time. So the particle content is you extend the standard model symmetry gauge group to an SU2 right doublet. So you make an left-handed particles charged under doublet and make an right-handed particles charged under the another doublet. So this becomes symmetry. And in this case, everything has its symmetry partner, like Higgs has an Higgs R. Quark has a quark bar. I'm using the YL notation, the two-component YL notation. Uh, the lepton doublets, quark singlet, lepton doublets, right? So you have the couple coupling, you can see up type coupling, you can have R and L, down type R, down type L, electron R, electron L, right? So everything is symmetric. But now you can also have some extra direct mass term. This is allowed. So you no longer, this term doesn't rely on any kind of spontaneous symmetry breaking. It's just allowed, right? And in this case, the Fermi mass becomes like this. The mass is generated from the couple coupling, but also direct mass term. And in this case, if the couple coupling is dominating, standard model quark is Q bar, and the right-handed singlet is U bar. They have the mass like this. So this is pretty easy. And the mirror part has the Q bar doublet on the SU2 right, and U, which is a singlet, and you have YVR. But oppositely, if the direct maximum is dominating, then you can see, okay, the direct maximum here, right? The U and U bar is heavy, and the standard model fermions is Q and Q bar. Now the right-handed quark is the Q bar. It's doublet under the SU2 right. And in this case, the second one is typically favored. It's because in the first one, the standard model singlet is given by this, right? And the any exotic quarks are given by YVR. So collider constraint is searching for these kind of exotic quarks are pushing the VR to be super high energy scale because the up quark we call coupling is really, really tiny. You want to have a large enough YVR to create a heavy enough fermions to avoid the collider constraint. But for the latter one, it's not. You just make the direct mass arbitrarily heavy, so the exotic fermions are this. And you want to search for that, okay, but that doesn't put on any constraint of VR. So in parity, this forces the Yukawa matrix to be like this, and then as becomes zero, and that also forbids the tutor. So strong PCC problem solved. And the symmetry breaking pattern is, and now you have an extra step. The Higgs VR becomes like this, right? They have a VR and that breaks the high energy scale gauge group down to the standard gauge group. And this is like an electroweak-like process. And in this process, we have a gauge, you have gauge bosons. You have WR, you have ZR, right? And now LHC can search for this kind of new gauge bosons. And for example, the mass of the WR is constrained to be heavier than 6 TeV. So that is translating to VR to be heavier than 14 TeV. And that's the current status of the stress and of this kind of parasymmetric models. And the limitations is like this. You are searching for everything. Everything is heavy. You're searching for heavy particles. And the problem is you're only searching from below. Everything is bounded from below. There's no upper bound. As long as the theory says everything heavy enough, you're done. You couldn't see that. And that doesn't automatically comes with dark matter candidate. Again, you see a lot of extra particles, but amazingly, none of them are good dark matter candidate. That is a problem. So today I'm going to talk about how to solve this. You have to add some extra fermions for a dark matter candidate from the freeze-out mechanism, and you will be able to see that this kind of dark matter candidates will automatically comes with an upper bound of VR. So let's go. Uh, I'm going to start with some kind of minimal representations. For example, electroweak doublet, and now you embed them into the parity symmetric theories and the right-hand doublet like this. So you have a pair of doublets. Or you can embed it as a bidoublet, right? Or you can have a bitriplet. So unfortunately, bidoublet is excluded. I'm sorry to see that, but that's true. A doublet pair and the bitriplet are interesting, and I'm going to cover it in this talk. So the doublet pair is like this. After the VR symmetry breaking, the psi r becomes the neutral part and the charged part, right? And the neutral part is singlet under any standard model gauge group. Psi L is still here. And after the symmetry breaking of the electroweak symmetry breaking, psi L is bliss. But now remember, these two are from psi L, so they are SU2L doublets. W boson still connects these two. And the psi R is really neutral, but that's dark matter. You may say, oh, why are the mass difference are the mass different? Dark matter should be the lightest one, right? And I'm telling you, yes. Because after the VR symmetry breaking, you have these three eigenstate, right? And you run the mass parameter from VR down to the all the way down to electroweak scale. And the running is different for these three mass eigenstates, for these three gauge multiplied eigenstates, right? And that could create the mass splitting. So you can calculate it. Okay, psi r minus, which is the charge component of the psi r, compared to the dark matter, it has like 100 GeV or so mass difference. And the psi L is even stronger, right? Because that has more charges on the more everything else, on everything else. So you have it. And the freeze out is just a standard freeze out mechanism, but you have to ask the question is, psi L and psi R are two different states. Do they co-annihilate with each other? So that is a question. And naively, you would say no, probably because they just don't connect with each other, but you can have this kind of high dimension operators. And if the scale is reasonably low, you can see, okay, this connection is probably strong enough, and we can have it during the freeze-out mechanism. So it's a co-annihilation. Otherwise, it's non-co-annihilation, right? So, sure, this is 10 to the order 11 GeV or 10 to the 9 GeV, depends on mass splitting compared to the Z boson. Yes, that's the case. So, uh, and we can estimate and quickly show that, okay, this leads to some kind of psi L decay, and the decay is earlier than BBN, so it's fine. There's no ineffective bound. So in this case, for example, you talk about co-annihilation, and I say, okay, you have a regular annihilation branch, but you also have a resonant annihilation via the WR and the ZR. For a non-co-annihilation case, sorry, I had a typo on the title, but this is a non-co-annihilation. For a non-co-annihilation case, the right-hand part still have a W boson resonance, double boson resonance. But the left part, which is the orange dashed line, only have a Z boson resonance. And the total of them only have a Z boson resonance here, right? So in both cases, you have resonance, this kind of dip. And as the VR goes higher and higher, the dips becomes shallower and shallower because the high VR is even suppressing the annihilation cross-section via the resonance. And if it's high enough, even the resonance dip couldn't annihilate the dark matter enough, and that will overclose the universe. So that provides an upper bound of VR, and that's what we're trying to talk about, right? So in this case, we just plot the VR versus psi, which is the dark matter mass plane. You calculate the dark matter abundance, you will see that. Okay, for a co-annihilation case, this is a W resonance branch. You can see the upper bound for VR is around 60 TeV. And here is around 48 TeV, right? And this is the Z boson branch. For non-correlation, you only have one resonance branch, and that is 26 TeV. That's what we're going to that is what I want to say, right? So you can have constraint other than the colliders, you have the direct action and indirect actions, which is what I want to say. So direct detection. You can have the coupling to the ZR, and you can have this kind of scattering diagram with the nucleons, so you can have direct detections. Uh, well, the good news is DR, ZR suppresses the cross sections. So you're not excluded. You're not done, right? So you can see this kind of things. The heavier the VR is, the smaller the scattering cross section is. So, but future projection still provides a very promising thing that it can cover almost everything here, right? And indirect detection is another story. Well, for sure it can have this kind of signals, right? Well, the problem is uh, this is the ionospheric profile. This is inevitable profile. And we know that indirect detection really depends on the dark matter distribution profile, which is not known for now. And the uncertainty could be different by orders of magnitude. And that is the current status, unfortunately. And if we assume the most stringent profile, which is ionospheric profile, you can see the current cross-section is just slightly excluded by an order of factor. If you assume slightly weaker profile in FW profile, so one of the branches there. And if you assume a weaker profile, the constraint is just gone. And as you can see from the left panel, you can see, right, this is 2, and this is just 1, just a factor of 2, right? So that's the current case. And I'm saying people really needs to improve the indirect detection and try to calculate these kind of profiles to reduce the uncertainties. Otherwise, we'll never know whether this is included or not. And this, unfortunately, that's current status. It's the most stringent, which may be not likely profile, barely touches the cross sections. So we motivate for some kind of future detection on this. So let's make a short summary for the doublet pair scenarios. So now the upper limit is not the Planck scale, but the dark matter relic abundance requirement pushes the upper limit for VR down to like a few tens of TeV, and the lower bound is provided by direct sections or colliders. So we're going to close this. And the dark matter annihilation is mainly by the resonance annihilation with the W boson and Z boson, the new W boson and Z boson. And that kind of things are automatically coming in the parity-symmetric theories, right? So everything is pretty natural. Well, because we have this kind of framework and this framework is pretty general for all the representations that I want to consider, I'm going to say I'm going to say very quick for the remaining things because you can just apply this kind of framework for any kind of representation here. For example, the bidoublet, that is excluded for a very simple reason. Now it's bidoublet. So psi becomes like this, 1, 2, and 1 or 2. This is a doublet, weak doublet. And dark matter is 1, 0. But note, this is from a weak doublet. It's doublet. So it still couples to Z. So if it couples Z, then the direct section cross section is just huge. You're just excluded, right? So, and the bitriplet is a different story. It's a weak triplet. So it's a Wino-like particle, and we know that the weak triplet has a neutral component that doesn't couple to Z. And now we just don't have a direct action. There's no way. Now you have, and the story is you can have WR between these two different components, and now you always have co-annihilation, right? So the result is like this. Traditionally, we know that is without the resonance annihilation. We know it's 2.9 but here, because of the extra degrees of freedom, this regular annihilation branch becomes 2.4 It's slightly less than we know. And the resonance branch is still here. The upper bound for double branch is 170 and this is like 100 right? So, and unfortunately, the constraint is from LRC. And you can also talk about indirect action, and the difference here is the neutral component of dark matter annihilation is just W. It's just we know with T-channel fermions goes to WW, and that's independent of VR, completely independent of VR. So you can just plot the annihilation cross section as a function of the M chi, the dark matter, and you see, sure, is that excluded? Oh, well, it depends on where you are, right? Because now all the masses are possible to produce a dark matter out of abundance. Depends on VR, right? But if you assume the most stringent profile again, you will see, that is excluding everything. But if you assume a weaker profile, that's not. As you can see, the bottom part, this part is still only by a factor of few above the current constraint, assuming the most stringent profile. If you assume a weaker profile, probably like here, probably like here. So you have plenty of open prime space by that. But another conclusion is this is traditional we know. But now we know it's shifted to the left. For example, here. If you go here, then that is even more disfavored. Like you could assume a weakest profile probably that's still allowed, but now it's strongly disfavored. So that's the impact, right? And again, in this case, I would encourage people to do more things about indirect detections to reduce the uncertainties of the profiles and improve the accuracy of the measurement so that you can tell me whether these bottom parts are really excluded or not. And again, this is only assuming the strongest profile, which is not sure and probably not likely. So uh, a conclusion for today's talk is it's kind of very straightforward idea. You just add the fermion candidate, dark matter candidate to the parametric theories. Uh, and in this case, you talk about the standard freeze-out mechanism, and you can, in this case, you can see, oh, there's an upper bound for VR because you want to have the correct dark matter relic abundance. And the complementary from the bottom is Kaleido searches. Direct actions, and probably I want to encourage people to work on indirect actions to improve everything. So, uh, thanks for listening. I'm opening for questions and discussions. Thanks for holding this work.